Hello everyone, welcome back to JP Science. This is part 3 of adding and subtracting two-dimensional vectors using components. Okay, so let me remind you of our 3 steps in order to do this. Okay. And then in this video, we're going to be adding vector E and vector F. Okay, so let's get started. The first step is to find the magnitude of the x and y components of our vectors. Okay, so that's the x component of vector E. Vector E. That's the x component for vector F, the y component for vector E, and the y component for vector F. Okay, so let's go find the magnitudes for those components. Starting with vector E, the x component's magnitude is going to be found by multiplying the magnitude of vector E by the cosine of the angle between the x-axis and the vector. Okay, so in this case, that's 20 degrees. And the magnitude of vector E is 10 newtons. It's going to be 10 newtons times cosine 20. Okay. For the y component, it's going to be the magnitude of vector E multiplied by sine of the angle between the x-axis and the vector. So the y component's magnitude will be 10 newtons times cosine 20. When I plug that into the calculator, I get the x component's magnitude to be approximately 9.397 and the y component's magnitude to be 3.420. So the same thing for vector F. The x component's magnitude is going to be the magnitude of vector F multiplied by cosine of the angle. So that's going to be 12 newtons times cosine 70 degrees. And the y component's magnitude is going to be the magnitude of vector F multiplied by sine of the angle, okay, which gives us this. And if I plug this into a calculator, then I get approximately 4.104 for the x component's magnitude and 11.276 for the y component's magnitude, okay? And let's not forget to put our units, which is newtons, here as well for E's components. So now that we have the magnitudes of the x and y components for vector E and vector F, we're going to add the x components together and the y components together to find the resultant vectors x and y component. So we're looking for the resultant vectors x and the resultant vectors y component. And the resultant vectors x component is composed of vector E's x component and vector F's x component, right? And then the resultant vectors y component is composed of vector E's y component and vector F's y component, which is why we're going to do this right here to find the resultant vectors x and y components. So let's go ahead and find the x component of our resultant vector. Okay. Now, one thing we do have to note is that both the x components of vector E and vector F are going to the left, right? They're going in the leftwards direction, which is the negative direction. And so in this case, instead of putting just 9.397, which is the magnitude, we have to put negative 9.397. Okay, plus negative 4.104 newtons. Okay, and that gives us negative 13.5 newtons for the x component of the resultant vector. Okay, and then for the y component of the resultant vector, same thing, because vector E and vector F's x components, y components are pointing downwards, they need to be negative when we do this. So we're going to do negative 3.420 newtons plus negative 11.276 newtons, which comes out to negative 14.7 newtons. Okay, so there's the x and the y component. And as expected, they're both negative, which means that our resultant vector is going to be somewhere here in the third quadrant. Okay, so our last step would be to take the x and y component of the resultant vector and find the magnitude of the resultant vector itself. Okay, and to do that, we're going to do the square root of the x component squared plus the y component squared, right? And so this would be negative 13.5 newtons squared plus negative 14.7 newtons squared, okay? And that gives us 19.96 newtons, but we're going to approximate that to just be 20 newtons, okay? And then now, we're going to find the direction of our resultant vector. And to do that, we do the inverse tangent of the y component divided by the x component. And so that'll be the inverse tangent of negative 14.7 newtons over negative 13.5 newtons. Okay, and that comes out to just about 47 degrees. Okay, now this angle is the angle between this negative x-axis and our resultant vector, so that angle right there. If we would say that the resultant vector's direction angle is 47 degrees and said that that's our answer, or something like 47 degrees above the horizontal, that would actually be incorrect, because when we say that the direction angle is 47 degrees, we measure always from the positive x-axis. And so based on our resultant vector's x and y components, we know that the resultant vector is here in the third quadrant, but saying that the direction angle itself is 47 degrees, or 47 degrees above the horizontal, would indicate that our resultant vector is somewhere here in the first quadrant. And so that would be incorrect. And we actually have to find the angle from the positive x-axis. Okay, so let's say that we use 47 degrees, not as our direction angle, but just as a reference, right? We know that it's 47 degrees. And so starting from the positive x-axis, if we go to the negative x-axis, it's 180 degrees. And then from the 180 degrees, we can add the 47 to find the true direction angle. So in that case, we would do 180 plus 47 to get 227 degrees as the angle that represents the direction of our resultant vector. Okay, now this angle is positive because when we go counterclockwise from the positive x-axis, we measure with a positive angle. And when we go clockwise, then we use a negative angle. So the direction angle can either be described as 227 degrees, I guess from the positive x-axis, or we can also find this angle here, okay, which is 133 degrees, and say that the angle is negative 133 degrees. Again, because we're going clockwise from the positive x-axis. So these are both correct. And let me mark this with an R just to show that this is our reference angle. And the direction angle is either, like I said, 227 degrees or negative 133 degrees. Okay, and so to express the answer, we would say that the resultant vector has a magnitude of 20 newtons and a direction of 227 degrees from the positive x-axis. What if instead of both the x and y component of our resultant vector being negative, what if one of them was positive? So let's just say maybe our x component is positive. Okay, then if I drew this in red here, then you would have a positive x component, and then the y component, let's just say, is still negative. Sorry, let me draw that a little longer since 14.7 is indeed greater than 13.5. So it should look something like this, our resultant vector, okay? Now, in this case, okay, I want to talk about how we're going to find the angle, okay? So the magnitude is actually going to be the same. As you can see here, even if we make the 13.5 positive, it doesn't change anything. It's still going to be, the magnitude is still going to be 20 newtons, okay? Now, what does change, though, is that when we search for our, what we now call the reference angle, we're actually going to get something a little bit different. So the inverse tangent of negative 14.7 newtons over positive 13.5 newtons is going to give you negative 47 degrees, okay? Now, in this case, just like if we had a vector in the first quadrant, the reference angle is actually going to be the same as the direction angle. So the direction angle we can represent as just being negative 47 degrees, because as you know, when we measure clockwise from the positive x-axis, we get a negative measurement, and so this itself is the 47 degrees. Now, alternatively, if we wanted to represent this as a positive value, we could do 360 degrees minus 47 to get 313 degrees, and so the direction angle could also be written as positive 313 degrees, which would be from the x-axis going counterclockwise all the way to our vector. Okay, and so in this case, our resultant vector has a magnitude of 20 newtons and a direction angle of 313 degrees from the positive x-axis. So the last situation we're going to look at is if the x component was negative and the y component was positive. Okay, so if we graphed it, this would be the x component, the y component would be there, and so our vector, our resultant vector, would be here in the second quadrant. Okay, so let's go ahead and find this reference angle here. Okay, So remember,
In
the
order to
angle
not-
is going to be the inverse tangent. So the reference angle is going to be the inverse tangent of, this time it's positive 14.7 newtons divided by negative 13.5 newtons. And this gives you negative 47. Okay. Now, in that last example, negative 47, which is our reference angle, also was just the direction angle, because negative 47 from the positive x-axis would be here in the fourth quadrant, and that'd be correct. Okay. However, now this negative 47 does not describe our resultant vector's direction properly, because our resultant vector is in the second quadrant. Okay. So remember that this is a reference angle, and so measuring from the positive x-axis, there's 180 degrees in the negative direction, the clockwise direction, before we actually encountered this 47-degree reference angle. So the true direction angle is going to be 180 degrees plus the 47 to give us 227, or in this case, it's negative 227, because we're measuring clockwise from the positive x-axis. Or if we measured from the positive x-axis counterclockwise, then our angle would be positive 133 degrees. Okay, so now in this case, the reference angle is not the same as the direction angles, and so the resultant vector has a magnitude of 20 newtons and is 133 degrees from the positive x-axis. Okay, and for all of these, I gave the positive angle, but if you wrote the negative angle, that would also be perfectly fine and would be correct as well.